You're listening to Gradient Dissent, a show about making machine learning work in the real world, and I'm your host, Lucas Bewald. Edo Liberty is the founder and CEO of Pinecone, which is the leading vector database for machine learning applications. Previously, he was leading research at Amazon AI Labs and Yahoo's New York lab. He's got to be one of the world's experts on vector databases, and we talk about everything from the trade-offs of building vector databases to the applications that are built on top of them to what motivates him personally. I hope you enjoyed this episode. All right, man. Well, thanks for taking the time to do this. Obviously, you're the founder and CEO of Pinecone, so I feel like we better start with an explanation of what that is and generally what a vector database is.
Sure. Glad we're chatting. Pinecone is the de facto standard in cloud vector databases now. And vector databases are the way that large language models access information. And so people try to make their AI knowledgeable, whether it's semantic search or chat or what's called RAG, or trivial augmented generation. The tool of choice is a vector database, and within that, the tool of choice is almost always Pinecone.
Nice. Well, let's get a little more specific. Can you describe how they work?
Sure. So vector databases really are a new kind of database that is actually used more like a search engine than a database often, where objects are represented by what's called a vector, which is an array of numbers. So it's like literally a float array. And that is the numeric representation that foundational models, large language models, multimodal models give to any object, whether it's an image or an audio snippet or a piece of text, that encode the meaning of that object. In some sense, what does it say? What does it stand for? What does it contain? And so on. Okay. And the role of the vector database is to be able to retrieve similar objects, things that mean the same, that contain the same topics, that contain the same content, that are relevant to some question, that align or associate with some task. And because of this numeric representation, because of this like fuzzy matching, you can now retrieve over very large amounts of data relevant information. So you can build question answering, for example, and make it very knowledgeable over your own company data extremely easily and efficiently, which you couldn't do before.
And so the challenge here is you're trying to find the set of numbers that are kind of closest to another set of numbers. Is that right? Like you sort of...
Yep, that's pretty much it. You nailed it. That's everything we do. Think about that as, so this is the basic function. You're right. I mean, in the sense that you can think about alignment of these arrays. Think about arrays as vectors or sequences of numbers. You can ask yourself how aligned they are, or if you look at them as vectors in high-dimensional space, what's the angle between them? You say, hey, or what's the distance between them? You say, hey, retrieve everything from some area of space, or some small angle around what I'm looking for. But first of all, that alone becomes exceedingly hard when you have hundreds of millions or billions of these vectors, and you want to do this efficiently and quickly and at cost. But you add to that the need to filter by metadata, the need to boost by keywords and other like sparse signals. So you want to now change the score, the ability to do that, at bursts of queries with low latency, and sometimes do this very infrequently, and so on. So you really have to build a very, very complex system that can organize data correctly, index it correctly, access it correctly, and so on.
Can you describe, like, for that kind of fundamental task of, kind of finding the closest vector by some metric to another metric, like, how do you even get started with that? Like, what's the most basic way that you would implement a vector database?
I'll start by saying that I have, in my career alone, built quite a few different systems that needed to do something like this. And so ad serving in Google and feed ranking at Facebook and shopping recommendation at Amazon and you name it, all use vector search behind the scenes to some capacity. Okay, and of course, thousands of other applications as well, not just those, right? There isn't one way to implement it. And in some sense, that's what's so exciting about building a company like Pinecone. We can automate, we can experiment, we can implement hundreds of different techniques and figure out what works best and optimize and so on. It's a very interesting engineering problem. But if you want to just simulate what's the basic thing, you can literally take a NumPy array as your matrix of vectors and literally compute the, say, cosine similarity of Euclidean distance, literally the sum of distances squared from your query, and just take a threshold. In fact, my LinkedIn profile, for a while, my title was like a one-liner in Python that did vector search.
Nice.
It's like that was like, after a while, people told me, what the hell is this nonsense? I'm like, okay, maybe I'm just confusing people. I thought he was clever, but maybe... maybe the people thought he was either obnoxious or enigmatic. So he I stopped with it. So you can't do it in a naive way. It's just extremely slow and inefficient, extremely memory consuming. And of course, when you run these things at scale, of course you can't do it on your laptop. And of course you can't do it in Python either.
So, like, what are the first optimizations that you would think of, and what are like the big trade-offs of the different ways you could approach the problem?
So there are many different optimization functions that you might think about. Well, optimization function, I don't mean mathematically, I mean as an operator, right? Are you minimizing latency? Are you minimizing cost? Are you minimizing operational, complexity and overhead, right? Are you maximizing throughput? I mean, there's like, again, as every engine, you really have to figure out what it is that you're trying to do. The vast majority of libraries for vector search out there really only optimize for, sometimes really minimize latency, but not always. Like really maximizing throughput is in some sense became, I don't know why, the main competition, right? Mm-hmm. I can tell you that we at Pinecone, even though we ran a competition called Big ANN in which we benchmarked these and we open it as an academic competition, ran it, we actually participated as well, and we actually dominated, of course, all the tracks, which is maybe not surprising because we were professionals. This is an academic competition. Mm-hmm. But this was just to make the point that throughput is interesting as an academic exercise. It's not what most people care about. Mm-hmm. The vast majority of our customers don't really care if they get 1,000 queries per second or 2,000 queries per second on a single core, or like whatever, on a single machine. Because they don't have that throughput. Mm-hmm. Right? They might have 5 queries per second, okay, or 10 for each index, for each small index. And B, because they don't run the hardware, they usually manage servers. So they really don't care how much hardware we use behind the scenes. They just care about how much it costs. So we figured, hey, okay, fine, we get it. So we optimized for 2 things. We optimized for cost, and then we optimized for ease of use. Mm-hmm. And what we launched last month, almost exactly a month ago, is the serverless offering for Pinecone, which seems like, okay, you just took your engine and made it serverless, but it's not that at all. We actually had to rebuild almost everything from scratch to be completely supported in a serverless way. Okay, and we had to. I'd love to tell you what we did differently, but the outcome is that this is 10 to sometimes 50 times cheaper for most workloads. And it's completely hands-free. So you don't have to choose hardware or algorithms or anything. You've started index without saying anything, and you just push data to it, and it says, great. And it doesn't matter if it's 100 vectors or 100 million or 100 billion. I mean, it matters to us. It doesn't matter to you as a customer. For us, it matters a lot.
Well, look, I mean, so that's amazing, and I want to get to that, but I feel like I'm like at a little bit more of like a basic level than you. Like I vaguely remember my like databases class, and I can kind of understand for, search how you can create an index, and then the latency like won't scale linearly with the amount of data that you put in. But if you have to compute like the dot product of your vector with every single vector in your database, how do you keep the database from getting slower when you have like, 100 million and then you go up to a billion? How do you keep it from getting 10 times slower each time you scale the size of your database by a factor of 10?
So one of the things we're doing, and this is one of the hardest architectural feats in serverless, was the fact that as data comes in, we in fact process it with a very highly specialized write path that actually augments small files in blob storage that contain vectors that are likely to be queried together. If it's Euclidean distance, they may be close. If it's angular distance, they might be within some cone. And it's in fact very hard to do at large scale. So it's easy to do on 1,000 vectors. It's very hard to do when you have 10 billion or 100 billion. To keep all of that in check and organized in blob storage and keeping a very good, keeping track of what is where is actually incredibly complex, right? So that's one part of it. And the second part of it is a query planner. The given a query now has, in some sense, like a model for each file, and says, oh, out of the 10,000 files that you have, each one of them might contain a few thousand vectors. You can even just look at these 100, right? And with all likelihood, they'll contain the top results you look for, right? So they might not all the time, but usually they would, and that's when we start talking about like recall and the accuracy and so on. So you have to trade off a little bit of accuracy for your speed. But if you do this well, you can look at a tiny fraction of the data and get almost all the results that you want. Some usually, literally all of them. And as a system, you need to also have the whole caching hierarchy done really well. So the vast majority of the data is actually dormant and in blob storage, and you never touch it. It never costs you anything. And the small amount of data that is hot actually gets propagated to SSDs and into memory and so on. So you can actually be very, very reactive. Does that answer your question?
Let me see if I understood it. I'll try to repeat it back to you. It sounds like you kind of break up the space into some like regions, and then each region kind of gets its own kind of mini file of the stuff in that region. And then when something comes in that you want to match, you like look for what region it is and just focus on that particular file that contains the vectors that are sort of in that area. Is that
that is correct in spirit, but it's actually a lot more complicated than that, because some vectors might actually appear in multiple places, in multiple files, because they have to for performance reasons. And some regions might overlap. Some regions might be contained in other regions and be bigger or smaller and so on. So it's not as simple as just divide the space, and each part of the space, like these points go there and these points go there. It's not quite as simple as that, but conceptually that's a right way to think about it.
And I guess if you have like a stream of new points coming in, do you have to then at some point stop and sort of like reallocate everything or kind of create a new index across this? Is that an issue?
So that's the beauty of and why I said it was very complicated to build that, because you can. I mean, you can always say, hey, I'll take some amount of data and then I'll just, after some period of time, I'll just recrunch everything, and that's it. And that's what some are doing. In some sense, that's a trivial thing to do, right? That ends up being incredibly expensive and incredibly slow, because that people have like these recompute like events when the data is bigger, and every time it gets bigger, it gets more expensive. And so in the beginning, it doesn't look very bad. And so when you have 100 million vectors, that's just, okay, it's annoying, but all right. But then you get to 1 billion and that thing takes a day and costs you $10,000. I'm like, holy shit, this is not acceptable. And then it goes to 10 billion and this thing costs $100,000. Okay, this is, okay, we have to rethink this thing.
Well, look, I mean, you've obviously been working on vector databases for a long time. And I was, having breakfast this morning with a friend who was talking about how he's like, yeah, you've been doing these vector databases way before it was cool. And we were wondering, like, did you sort of see these RAG applications coming in some sense? Like, I remember like there were embeddings before, GPT.
Yeah.
But at the same time, it does seem like, LLMs and GPT have really made an explosion of interest in it. Like, how did you think about that?
So I started saying that vector databases really use like search engines. They'll search for making AI more knowledgeable, and they're really used as information retrieval tools. And information retrieval existed for a long time before RAG. In fact, how RAG uses vector databases is a little bit like a search engine. You say, hey, give me everything all the documents that are relevant for this question. That's a search query in some sense, right? And that is put into the context of the LLM, and then answering the question becomes easier because you don't only have the question, you also have the reference documents from which you can take the answer, right? And so the answer is no, I didn't know RAG would be a thing, and I didn't know LLMs would become so good so fast. We did know that embeddings are becoming much better. We already saw in 2019 when I started Pinecone, language embeddings were getting dramatically better very quickly. GANs were already starting to be a lot better. Generation started happening. It wasn't great yet, but it was already surprisingly good compared to what existed before, right? And so it was clear that something dramatic is happening. I didn't know it would happen so fast and so dramatic. So this is so explosively. And I think, if somebody, maybe a handful of people at Google and OpenAI and others had known because they were working on it, but I think the rest of the market could know.
Mm. Do you have opinions on different embedding strategies? We have a lot of questions from our users that want to ask you about different things that have happened, like an uptake in interest on Colbert embeddings or OpenAI's new embeddings model that replaced the longstanding ADA 2. I don't know. Are you watching this, and do you have like recommendations for someone that was wondering what embeddings they should use?
So I do and I don't. So let me unpack that for a second. There was a flurry of activity from 2017-ish to 2020 something on creating of these like two-tower embeddings and like language embeddings and so on. BERT was making the rounds. Everything had to be with BERT, like Roberta, and I actually try to egg my research team to launch a BERT model called Liberty.
Nice, genius.
And I failed. They didn't want to do it. I mean, just for the pun, it wasn't motivating enough. By and large, these efforts have died down for two reasons. A, because the embedding models that are provided by the companies who do that became good enough. And B, because the efforts associated with training those models from scratch have gotten higher. So your ability to, in some sense, it's two sides of the same coin. Those models have gotten good and, good enough that you don't actually get a ton by one-upping them in some sense, and also one-upping them is terribly expensive and complicated at this point, right? So either people take it as a big mission to retrain those models, or they should just use what's given. So the one answer is, for the vast majority of people, don't train your own. Okay. Which one of my many collaborators in the industry should use? I will make a lot of people angry if I said anything. I will say that people
well,
use...
maybe rather than name a specific embedding, I understand why you don't want to do that.
There isn't one answer. I mean, different tasks require different embeddings, but usually it's experimentation. It's easy enough for people to go and switch out different models to see what works best for their application. That, in some sense, that question is like a hackathon level of effort away from you knowing the best answer for your product, right? Because they're all API driven. Just try 5 and see which one is best for you, right? And RAG, we see is actually a huge equalizer. So it's not only because it gives models the right context, the power of the model itself is less important. It's really more about summarization and creating a narrative around context they already have, which most foundational models are already very good at. And so it actually equalizes the quality almost completely. And so now it really becomes a question of speed and cost and maybe, a few % worth of difference in accuracy.
But it sounds like you also see people fine-tuning their own embeddings model. That's kind of interesting. Is that actually useful?
It is. It's not very common because it's not very easy, but it does happen and people do it. And in fact, we see that it does help. The main problem with it is actually operational and regulatory. Not regulatory, but governance related, data governance related. And companies who do that, either for some reason don't have that problem, maybe they use public data or something and they don't have that issue, or they actually spend a lot of energy resolving it. But when you fine tune a model, that data should be conceptually thought as being in the model being sort of like assuming the model has access to it, right? And there is no delete mechanism. You can't train a model and then say, hey, wait a second, please forget example 5,712 that you saw 5 hours ago. That function doesn't exist, right? And
I can see how that's like a huge problem with generating content, but is it as much of a problem with making an embedding? That seems like a little bit lower risk, doesn't it?
Not really, right? I mean, these numeric representations are, they're opaque to us as humans because we're not very good at looking at 1,000 floating point numbers and that making sense to us, right? Mm-hmm. But that's us. We're limited in that way. The models use that for example, for machine translation. You can take a sentence in French, mm-hmm. encode it, and then unencode it in English, right? Clearly, those numbers meant the same thing because you just took the numbers without knowing the original French sentence and translated it into English. And so the meaning is there, quote unquote, somewhere. I mean, how exactly it's there, we can talk and we can discuss what mechanisms encoded, but it's not information free. In fact, the whole point of using vector space and vector search and vector databases is because those representations are highly semantically valuable. They're very information rich, and so, in fact, we think they're more information rich than the original sentence, right? Because, that might, really not contain the meaning of the words or the synonyms or the context around it and so on. Does that help?
Yeah, totally. I mean, if I was fine-tuning my own embedding model, then every time I add data, do I need to recompute all the embeddings of everything that I want to search over, or is the change small enough?
Exactly. So this is another problem, right? If you change the model that generates the embeddings, then yes, you have to go back and regenerate all the embeddings for all the data that you have. So that's another reason why people usually stick with pre-trained models and don't change them at all.
Okay, well, I have the most softball question I've ever asked a guest on this show.
I love it. Bring it on.
I am really curious. Obviously, you guys have really stood out as the most used vector database in a really crowded space, including like every database company on the planet sort of saying that they're going to add or have added vector database capabilities. Like, what do you attribute to your success?
So I'll start by saying that we've been at it for a very long time, right? And this like serverless offering that we put out is, we internally call it V4, because it's the fourth time we have completely rethought how everything works and optimized the crap out of every possible part of our system, so that we can reduce cost and make it easier to operate and roll both of them into customers, right? So that relentless, pursuit of scale, higher scale, lower cost, easier to operate, higher scale, lower cost, easier to operate, takes a long time and a ton of effort, right? And we're delighted to do it. I mean, we're geeks. We love it. We will leave us to our own devices. We will spend a week with the Rust compiler and have a blast. Okay. But as companies grow around us, right, they view vectors as an add-on. They view it as like a hype in their document DB or in their keyword search engine or in their data lake or in whatever. And that's okay. I mean, yes, if you have embeddings next to some other data, great, fine, keep it wherever you want, Postgres or whatnot, right? But if you actually want to use that, you need something that's optimized for it, that's actually convenient for it, and it's plugged into the right tools and so on, right? And so that's where we shine. And we have teams that come to us all the time and say, hey, I thought that using, database, blah, I won't name any one of them, is going to be good enough because I tried it on, 1 million vectors and it worked fine. And I built some POC that my director of engineering was excited about. But now we're trying to scale it up and the whole thing just goes belly up, right? Or just becomes super expensive, or just latencies go completely haywire, whatever. And I'm like, yeah, what did you think? I mean, it's not it's a NoSQL database. It's designed for key value and for metadata. It's not designed for vectors, right? It's a key value. It's a keyword search engine. It's designed to search for keywords, not for vectors. I mean, it's a completely different thing. So, boiling all of it down is really, on the one hand, the fact that this is a completely new architecture. It's a completely new kind of tool built from the bottom up to do exactly this. And B, is just doing exactly maniacally focusing on this, only this infrastructure for now 5 years, has results.
I guess my understanding of the history of databases, which I'd be the first to admit I don't know super well, is that, there were kind of better closed source relational databases. And then over time, the open source ones kind of, won out just because like there's so many people working on it. Like, do you worry with all the enthusiasm around vector databases that, there's going to be tons of contributions to open source and they'll kind of get better and better? And of course, like, most of the people in the world aren't working at Pinecone. So you might expect them to sort of overtake you eventually.
So we can look at the history. First of all, we thought about this problem a lot, and
oh, sure.
Strategically deciding whether you want to be open source or closed source is a huge decision. It's a company defining decision. And in fact, it's almost impossible to reverse once you've gone one path. It's really like essentially a one-way door. Okay. We have chosen to go closed source for many reasons. So just for the history of databases, if you go back maybe 10 to 15 years, you really didn't have the adoption of cloud services where it is today. And so the vast majority of compute in the world and pretty much the whole target audience of most databases was on-prem or literally on like single, literally either compute clouds for large customers or just like server racks in their office, right? There, you really don't have, the only way to reach that audience is open source. And so you really want, if you want to put your product in the hands of engineers that know what they do without involving sales, the only way to do that is open source. So that became the wave of PLG. This is a product-led growth in the world before cloud. Okay, basically give your software to engineers, they'll figure out what to do with it. Come and visit them 6 months later after this is already in massive amount of usage in the company and sell them on your products, sell them on some services or whatnot, right? That completely changed with cloud because now it's actually much easier to consume a service than it is to consume open source. If I gave Pinecone the code base to somebody, they would think I'm nuts. Like it's tens of services and CI/CD pipelines and metering and whatever. Like it's a crazy machine, right? Nobody would even want the open source. They're like, "Are you nuts? You run this for me. Why should I run this?" Right? Mm-hmm. And as a result, the managed service ends up being so much easier to consume, and because all the AI companies and all the tech companies are forward-leaning and technology building, which is everybody in AI today. Nobody builds the next cutting edge of AI on-prem, right? They build it all in the cloud, right? Pretty much all of them prefer a managed service. And so that for me is the question. What do engineers want and how do we give it to them as fast as possible and make it as easy as possible to consume the best possible level of service, right? Now, you're right that there is a community aspect of open source that is very appealing, and there are other reasons why open source is fun and exciting, and there are other reasons why services are fun and exciting. I think they're secondary questions.
What do you mean they're secondary questions?
They're secondary questions in terms of the quality of the product, right? There's some people are open source fanatics. Fanatic sounds bad. They're all enthusiasts, I should say. It's not, there's no moral judgment. It's fine to love. I mean, I myself contribute to Apache projects and I'm very happy with open source. I have nothing against it. But if my team told me, hey, we're not going to consume S3, we're going to run the S3 code base ourselves, I would tell them, you've gone completely insane. Like this is, what's wrong with you? Why would you do that, right? I think, so that is, when I say secondary question, I mean, what is the right thing for the product and for the customer, and in some sense also for the company. And for us, we understand it's being a managed service. And once you do that, being open source doesn't actually add a lot of value. I'm saying it's whether it's open source or not is a secondary issue, because it does have secondary effects on community, on marketing, on positioning, on whatever, like on different channels and so on. Again, I'm not saying it's the same, but it's not significant, I don't think. Definitely not as significant as it was 15 years ago.
Okay, so one question a lot of our team had was, what have been the kind of optimization challenges and important technical trade-offs that you've made while developing Pinecone? And maybe I would add, how has that, changed? And it sounds like the 4 versions of your product, especially the serverless one that you've just launched.
So just like technical trade-offs, literally like in the weeds, like literally algorithmic or engineering trade-offs.
Yeah, I guess it sounds like there's always sort of like a latency versus throughput trade-off, I imagine. I sort of imagine that there's like maybe a trade-off between, in databases, kind of like the speed of writing and the speed of reading. Could be wrong. There's maybe a trade-off between sort of getting the exact right answer and sort of like the speed of returning something. Or maybe those are just levers that people could pull, on your database. Are there any sort of, I guess, is that the right mental model to have of your product?
It is. So I'll just kind of maybe list the tenets of us like developing how we think about what needs to guide our engineering decisions. I'm happy to dive into examples of what I mean by that, but you're right. There are trade-offs between accuracy and speed or latency, between ease of use and customizability, between so on. So we can kind of list all of that. We have decided to be very explicit and opinionated on one side of those issues. We want to be extremely easy to use, right? And so that means taking away levers, right? You don't get to choose the hardware. You don't get to choose the algorithms. You don't get to choose your 17 parameters that control how vector search works, right? Now, you can say, hey, don't you want to choose the algorithm for optimizing, I can squeeze out 5% more accuracy on this or that. And the answer is no, it's our job to figure that out. You need to not worry about it. You need to worry about developing your application, right? It's our job to monitor and view that and figure out, hey, something else needs to be optimized. We'll go and do that without you being in the loop. So ease of use. Scale, okay? Scaling is incredibly difficult, okay? Incredibly difficult to be done right. And if you don't plan for it, whatever, if you know you're going to run at very small scale, you can make a lot of really easy assumptions, right? I'm going to always run on one machine. I can stick all my data in memory. You can make a lot of really easy assumptions. We are always optimized for scale. Okay, when you create an index, we don't know, and you shouldn't care if you're going to put 1 million items in there or 1 billion items in there. In fact, it might be 10 million today, and tomorrow you're going to start adding 500,000 every day, and you're going to do that for 5 years, and you shouldn't care, right? Right. And so ease of use, scale, right? And accuracy. Okay. We understand that people need the latency and throughput and so on. It's very hard to control for accuracy. So we wanted to make sure the results are good enough and the accuracy is high enough, okay, that you shouldn't worry about it. And latency is something that is very easy to measure. Accuracy is actually hard to measure. It's hard to measure and it requires a lot of trust. And coming back to what we said in the beginning, doing this hard takes many years to actually perfect it and so on, right? One of the hardest things to do is actually to earn trust. And trust is, built over years and lost in minutes or immediately. We do everything we can to earn trust and make sure that people get good results on a consistent basis. And then everything else is, in some sense, secondary, right? Oh, and I forgot one of the most important ones is cost, obviously, right? I mean, so this is, again, you're using a managed service, you're trying to optimize for costs, right? And so some customers of ours sometimes come to me and say, hey, I really wish I could squeeze the lemon a little bit, or I want the ability to tell you, hey, for this index, do something slightly different and it'll be a little bit better. I say, yeah, I mean, that'd be nice, but would you want to do that like for it to cost like 3 times more? And they say, no. But by the way, not 3 times more because I will charge them, or just because whatever, it uses more memory or something. Like that changes the skew of the workload, right? Mm-hmm. And 99% of the time they say no. So we're very explicit on our choices.
Does any or how much of your success would you attribute to sort of fundamental insights in algorithms, versus just like kind of, getting a million details right?
It's a fantastic question. I'll attribute it to 3 things, really, but you're right. Algorithmic insights and acceleration and high performance, kind of the core of the engine, is incredibly complex and hard to do right, okay? But that's just one area, right? The second thing is really the cloud architecture and how you put everything together. This is not, again, talking about open source. Pinecone is not code. It's a live system. It's a multi-tenant, massive service running. Okay, that is incredibly, and it's incredibly complex to put. It's like, people say cloud native. Throw this around as a term, as like, I think this cheapens what it means. I mean, it's incredibly, like, the cost of networking of every subsystem and everything is modeled into this. So that is, again, took us years to perfect. And it's serverless actually takes it to a whole new level. It's a completely new architecture that I wish I could talk for hours about. It's fascinating. And I think the third, which is the most, in some sense, the most boring, but also the most valuable, is just operations. Half of my engineering team spends time on monitoring, on billing, on on-call support, on observability, on region deployments, on you name it, right? There's a huge amount of effort in just operationalizing such a system that supports thousands of customers in live. The people, on the one hand, fail to appreciate. On the other, I love that they fail to appreciate it, because it means that it just looks easy, and that means we're doing our job.
One of the trends that we've really felt in 2024, at Weights and Biases, is this shift towards multimodality. I think we were kind of overwhelmed by language applications for a few years, and now we see all kinds of things, right? Like, videos, images, audio, all kinds of interesting, like LiDAR and medical. Does that affect the way you think about your business at all, or is that kind of upstream from you and you just sort of like ingest embeddings?
I mean, it's mostly upstream for us. We try to run an unopinionated engine, and in fact, we have people use audio and video. People use us for pharma, for drug discovery on tissue molecule structures and protein structure and binding sites and so on. On complete documents, on parts of documents, on different kinds of text in different subdomains with embeddings of size 100 and embeddings of size 15,000. right? And so on the one hand, we're agnostic. On the other hand, those applications end up having different workload demands that we need to meet.
Like
so
what? What would change about the workload?
So one of the things is a lot of people build customer-facing products with us, right? And they need latency to be, 100 milli, 200 milli, 300 milli, right? If this was an analytical workload for just like drug discovery, say, right? And you really don't care if your analyst sits there for a second or 5 seconds, then that's a different requirement in the system than somebody like Notion who uses us for tens or hundreds of thousands of their own customers for Q&A. They're like, hey, when a user asks a question, the result needs to come back in sub-second, right? You can't wait 5 seconds. It needs to come back immediately. So we have to build a system that can deploy on, that query can come in. Their own user could be out of the system for 2 days and come back and ask one question. And their data might be completely dormant. And still this thing needs to be in front of them in less than a second. And we might have to deploy hundreds of CPUs to answer that question in sub-second, right? And fetch a lot of data, maybe from object storage and so on. So, for example, that customer-facing requirement is incredibly important. Customers have throughput issues and volume issues. Update, some data sets are updated all the time. If it's user-generated content. Oftentimes, if it's not user-generated content, you might have the whole data up front and it never changes and so on. So those kinds of workload dependencies are very, very domain-specific, while the vectors themselves don't change.
Are those places where you can actually give customers a lever to say, hey, I have a latency max that I'm willing to tolerate? Or do you somehow architect your system in a way that customer really doesn't have to think about that and they'll just sort of get high latency for any type of workload?
So we try to do the best that we can under the our pricing, that this feature that, I don't know if you see the thumb comes up. I speak with my hands. I keep getting gestures.
Do you have Zoom on? Can I do that? I don't know. It doesn't work for me.
Yeah, I don't know. No, so we try to minimize latency under the cost constraints that we operate on that are very strict, right? In what we see, customers are very happy with fresh data. So this is data that's queried constantly. Having queries having latencies of like 50, 100 milliseconds, and something that's like cold, something that, again, if you're like a RAG provider, I'll call you whatever. If you're a company building some application with RAG on a vector database for maybe 1,000 of your own customers, if one of those customers haven't used the system for a day and comes back in, right, you might be saying, okay, I'm fine with this like first query taking whatever, like 2 seconds, because, okay, fine, it's not a big problem. And then after that, it should be fast, right? So that's kind of the model we're operating on.
Got it. Okay. There's obviously the AI space is changing a lot right now. Are there trends that you're really watching because it sort of affects the way you operate?
Yeah, 100%. So, I mean, again, we started Pinecone in 2000. I started Pinecone in 2019 before RAG was a thing. The patterns of use change all the time. One thing that stays constant is people's desire to make machines more intelligent and more knowledgeable. If you want to make your AI knowledgeable today, that means using RAG in this way. And we're already seeing trends let's say, there's a lot more you can do, like re-ranking, like chunking different, like you asked about different models. There are models that now get specialized. So the models that are specialized in legal or medical domains, so on. Should we use those or should we not use those? And so on. So there's a whole list of improvements and ideas, and I think industry trends that will come to happen this year in improving quality. And at the same time, there are trends that have to do with governance and security and trustworthiness and the ability to reduce hallucinations and the requirements, sometimes some of the regulatory requirements to reduce hallucinations and so on. We'll see both of those, and both of those change our business significantly because the demands on our system become higher.
What are the most successful applications that you see right now built on top of Pinecone, and what do you sort of expect to see in the next year or two?
So it all comes down to being truly, for your AI to be truly knowledgeable. Again, we talked about that a little bit, right? Companies use it for legal documents, for their own, Notion uses it for their own, for their own customers' data, for them. I mean, not for Notion, but their own customers for their own company documents. Gong uses it for transcribed sales calls and getting insights out of those, and Semantic is searching through those. I can go on and on. People transcribing and searching and getting chatbots to be intelligent.
Look, I guess I was hoping that you could sort of like bucket them in your mind and tell me what the biggest buckets are. Like obviously, like I've heard of these, but if I just show up as a customer, what are like the top 2 or 3 things you would expect me to be doing?
So look, I mean, RAG is a huge. It's probably one of the biggest use cases right now.
But like RAG applied to what? Like are you seeing like companies doing this?
This is where I think this splinters off, and in some sense, why this is so interesting. I think RAG is a catch-all thing to get some relevant text and put it in front of an LLM, right? And I've been saying for a long time that text doesn't exist. There's no such thing as text because people because I'm trying to shock the system a little bit. It's because people tell me, oh, there's text and audio and video. I'm like, what's text? Text is emails, it's Slack messages, it's Twitter posts, it's Jira tickets, it's legal documents, it's medical transcriptions, it's sales calls. I mean, the content is different. What you want to do with it is different. The products you build with this are different. The insights are different. Like everything is different, right? There's the fact that we save them as .txt files means absolutely nothing to the application builder, right? And so for me, RAG is a very general framework. In fact, I spoke with an image search company that does image generation, like a generative, it's a generative AI for image generation. Okay, and they're building a model for it. And I try to describe to them how retrieval should be, in my opinion, used in their framework, right? And I basically described it as RAG, right? They're like, oh, it's not RAG, it's images. I'm like, what? So what? I mean, if you can retrieve 5,000 relevant images and out of those build an image, why is this not RAG? Because it's not text, right? And so oh yeah, that makes sense, And so, I think RAG is a very general thing, and it's what's happening predominantly now. We see semantic search as still being a very big use case. Anomaly detection being, anomaly detection, recommendation, others sort of taking, I think, a kind of a passenger seat for a little bit.
Is there any generic advice that you would give to somebody kind of wants to start a startup, doing some kind of AI application? Like, is there a place that you would point them that seems extra interesting right now?
I'm always tempted to give the same advice to startup people who want to start a startup, which is don't. It's almost always a bad idea.
Totally.
But I will say that I can tell you what not to do. And again, this is, I have this is my opinion. Okay, my 2 cents on what not to do. There is a pattern I've seen that people think that, I can use this and this model to do X, Y, Z, and it's going to be easy. Okay. I can do this and this, that, whatever. Like, I'll take this and I'll hook it in here, and I'll call an API call, I'll put it in front of a customer, and then I'll build a company out of that. It's wrong in 2 ways. A, it's going to be much harder than you think. Not building the POC, building the company. Building a company takes many years, and you need to care deeply about your customers and about your product and about your problem. If you don't care deeply and become a world expert in it, your product would suck. And B, if you're so lucky and somehow building that product was easy, then you would also be completely disrupted like 5 minutes later by somebody else that does exactly the same goddamn. Right? And so in some sense, you choose to open a company because it's hard, because it's something you're so passionate about that you're willing to invest a decade of your life doing, even though you know it's going to be like a monumental amount of effort, right? If that's the case, and an LLM is a part of it, go for it. That's the right thing. If you're doing it because you think it's going to be easy, it's going to be also, the likelihood of that succeeding is very low, in my opinion.
Well, that's a good segue into my second to last question here, which is, on a personal level, what's driving you at this point? What gets you out of bed to keep working on Pinecone?
The fact that we barely got started, man. I mean, we have stuff on the roadmap that I have been wanting to do since before we started. Okay. There is so much to be done yet. And in fact,
give me some examples. Let's
so I'll give you an example. We loaded all of a good chunk of the internet, all of Common Core. So we basically scraped, chunked, and vectorized the internet and put it into a Pinecone index and use that as RAG support different LLMs on factual questions from data. Okay. We saw that reduced hallucination on all models, including GPT-4, by roughly 50%. Okay. And we need to be very careful when I state that and exactly how we measured and so on. And there's a lot of information in the blog post that we put online on how we did all of that and so on. And so I hope people don't, latch on to this detail or that. So all the details are out there. Okay.
Mm-hmm. And sorry, what exactly did you do here? How did this work?
So we vectorized web pages from Common Crawl. You know Common
Right.
Crawl?
Of course, yeah. I get that part, but then how did you use that database?
Correct. So this is the interesting thing, right? When you now get a query for, say, a factual question, right? Mm-hmm. You can ask yourself, okay, now I know what that factual question, what the answer was. Because, we know what the answer is because we generated the answer from some page from Common. So we know what we should answer, right? Mm-hmm. So now you can give it to an LLM and ask that question without RAG, without context, and see how accurate the result is. Or you can add the LLM and add the vector database with RAG and give, in some sense, the LLM access to the internet through vector search, right? The difference ends up being reducing hallucinations for uh, uh, GPT-4 by roughly 50%, which is, again, I shouldn't say hallucinations. This is where details matter. You increase usefulness from 70% to something like 85%, or reduce unusefulness from 30% to roughly 15%. And for something to be useful, it's not enough for it to not hallucinate. It also shouldn't say, I don't know. Because I don't know is not a hallucination, but it's also not help. Right?
Totally.
And so you want to see that you get a factual answer, right? That required a lot of work and a lot of innovation on exactly how the search is done and exactly what you do with the results and so on. And in fact, the ability to really drive more knowledgeable AI and the ability the understanding that, hey, wait a second, you can actually make agents and support bots and all the RAG applications people build with us, make them a hell of a lot better by supporting the ecosystem better, by providing more features. That is incredibly exciting, right?
So you want to provide your own database that anyone can use, where I can just sort of query the general web or the common crawl? Am I understanding what you're doing?
We're not supporting that. We might. That's not a bad idea. But we're not supporting that. All I'm saying is the unlocked value. So the power of foundational models next to vector databases as a knowledge base is very far from being tapped. Okay.
Yeah.
See, our ability to build both the vector database and the foundational models and the intersection between them, the interaction between them, right? The ability to do that well and to understand all the trade-offs, we as a society are very far from understanding it. And we already know, because we already have experiments in the lab that show that there is a huge gap between where the world is at right now and what our customers do right now and what we can already see is possible, right? And so the question is, how do we get people from here to here? And hopefully in the same period of time, our research is going to go from here to there, and we can already chart 2 years into the future again.
Okay, that's actually a great segue to my last question for you, which is, what's the hardest part about getting these RAG-powered applications into production? Because I think where we sit at Weights and Biases, we see a ton of people that have kind of amazing prototypes, and they're sort of getting ready to do this. But I'm sure there's more issues than just, kind of getting the vector database right and making sure the latency is low enough. Where do you see your customers run into unexpected issues?
Well, maybe they're unexpected to them. They're not unexpected to us.
Totally, yeah. Unexpected to them. Absolutely.
Yes, exactly. So I'll just start by saying that unexpected is exactly the right word, because it's a question of expectation. Okay. People have gotten used to the fact, or at least AI has gotten so good at the marketing around AI has gotten so good that people expect everything to just work perfectly out of the box with one API call, and that's it, right? And that's not how the world works. If you build a legal support tool on legal documents, right? You'll have to figure out how to do it. You'll have to build a chunk and embed documents and figure out how to connect all of this and build your application correctly and so on. That takes iteration. It's not a notebook example that you go through and everything works perfectly. I mean, yes, the water will go through the pipes, but then you'll put your own data and then you'll start improving on it. And that journey might take a few months of you experimenting and trying more things and getting insights and improving your product and so on. So there is a learning curve of using a new tool in your AI toolbox, right, in your AI stack, and learning how to use those foundation models and learning how to use vector databases and learning how to build RAG applications. like everything else, it's a skill. It's something that you learn how to do, and hopefully after you've done it once and it took you 3 months, the next time will take you 2 weeks, and maybe you become an expert in it and you can go and apply it in 100 different places. But I do see customers or potential customers struggling with the thought that I expected this to just work in like out of the box. And we come there's like, yeah, no, we sell you infrastructure that you go build amazing application over. And it's going to be an effort for you to become an expert on this. And it might not be years, but it's not a day either.
All right, Edo, we're up on time, but this is really great. Thank you so much.
My pleasure,
with that inspiring end.
I hope we're not ending on a downer. It's like...
No, I think everyone will relate to it, honestly. It was great. Appreciate it.
Cool, man.
Thanks so much for listening to this episode of Gradient Dissent. Please stay tuned for future episodes.